We're doing the pH scale and the calculations now. So this is the way of showing how strong an acid and base is. So this is a logarithmic scale. So pH 1 and 2 are not double. They're 10 times different from each other. And so 7 is considered neutral and higher than 7 basic and less than 7 acidic. But we need to go into a little bit more detail than that. So I've put this up here. So you need to have a general idea of common substances and how acidic and how basic they are. You also need to know the strong. You can see these are 1 molar here and 1 molar here. That's a strong acid, that's a strong base. That is considered a weak acid and a weak base, even though it is 10 times weaker in concentration. This is a very weak base. Going on from that, why do we have the pH scale? Because dealing with really small numbers such as here, or anything here, these are like 7 zeros. 1, 2, 3, 4, 5, 6, 10 to the minus 1, 2, 3, 4, 5, 6, 7. Those sort of numbers are very difficult to work with, and that's only halfway. It could go up to 10 to the minus 14. And so when we're dealing with pH, which is a measure of the hydrogen ion concentration, we need a way to convert those numbers into something that's easy. And all we do is we grab that little number there, and that becomes the real number. Okay? So the hydrogen ion concentration, which is not in your data booklet, is 10 to the minus pH. So if you want to know what the pH is, this one is, pH is a negative log of the hydrogen ion concentration. You have to do this calculation. For some reason, they think your logs are amazing, and you'll know this formula. So if you don't know, if your logs, I wouldn't even trust your logs. Just learn that formula as well, unfortunately. And you can see that hydroxide ions are reverse. We said 10 to the minus 3 is insignificant. As you can see, this is quite a large difference here. And so if you put them all together, you'll see that they always add up to the same number pH-wise. So I think this is jumping the gun a little bit. So the pOH and the pH will always add up to 14. But we won't worry about that right now. Okay, so the that's over in here. Okay, so they also want you to understand the pH graphs. So I've drawn in a pH graph here, and this one illustrates quite nicely. If you go from 6 to 7, you can see there's a 1,000 to about 100 drop. But when you go from 7 to 8, there's a lot less. So I think it's 100 to 10. That's what it's meant to be, but it kind of looks like that. But you can see it's quite extreme. It's a 10 times difference, not a double difference. And the reason, because that's what it is. It's log. They go up in tens by 10. Okay? So this is the one case where you can say it's a negative logarithmic relationship, because it is exactly that. And you're going to get pH. It doesn't take too strong values, really. As soon as you go over 1 molar liter, pH is actually going negative. So I think pH 2.5 or 2 molar, sulfuric acid 0.3. You have to plug the numbers in, minus 0.3. But you can see from a log graph that it does go negative, and it goes negative at 1. Okay, so be aware of those things as well. So negative pH values are a thing, okay? And so we're going to use these formulas. This one's in your data booklet, and this one is not, but you need to know how to use both. So the first question we're going to do one pH to hydrogen ion, then hydrogen ion to pH. So what's this one? pH to hydrogen ion. So write out the formula first, just to make sure it's 1:1. Okay, and then so you know that the hydrogen ion concentration must be the same as the concentration of the substance, because it's monoprotic. And then you write formula, substitute, and there's no units for pH, so you're done. That's the pH, 1.7. All right, so it's just a mathematical conversion of an uncomfortable number to something that's just between 1 and 14. That's quite easy to work with. This one's a little harder. So what is the concentration as sulfuric acid if pH is 2.5? So you write the formula out. It's diprotic. So equation. Then write out the formula, substitute, and there you go. That's the number of moles of hydrogen ion, but 1:2. So you write out that and do your cross multiplication. And so the final answer is 0.0016 moles per litre. There's a video on there with cabbage indicator, and that goes through some of these simple calculations, but it does also go into the high level concentration calculations with Rice diagrams. So watch that and be enlightened.